Welcome to the glass plate. In previous examples we've been considering heating up of water in a cooker. What we had was water sitting in a cooker that was electrically heated, so production of heat internally or heat flow into, it doesn't matter how you do it, it's the same idea. Heat comes into the water. Now we're going to look at if you keep on heating this up, eventually the water will reach boiling temperature, 100 degrees Celsius, and the water will start boiling. And thus you will lose water vapor out of the system. We start with our half a liter. And we assume that we have brought it to boiling temperature, so that part is done. Now we could ask ourselves, how quickly is this changing in level? How much water are we losing in the form of vapor? Let's first do a quick and dirty analysis. The energy required to turn liquid water into water vapor is called the enthalpy of boiling. And that is a number that you can look up. The enthalpy of evaporation actually is what we say, and that is 2.2 megajoules per kilogram is required. We have a power input here of 1 kilowatt. So let's do a quick and dirty estimate and then later refine it. We could say if we need to compute that all then and evaporate everything, then the total mass that we have needs to be evaporated, and thus you need this amount times the half kilogram that is sitting in as the energy for evaporation. And we put that in via our heater, and that produces a kilowatt of energy, the joules per second, and we need to switch that on for a time interval t. If this is the same amount as that is required, then everything is vaporized, assuming that there are no losses. And thus I can quickly see that T equals the mass times the evaporation energy divided by the power input, and that gives me 1100 seconds. Now this is an easy, kind of intuitive way to quickly do it. Can we do it with our balance equations? Of course we can. And I'm going to show you how. First we need to realize that if we set up a balance, and we think energy balance, that heat is flowing out here in the form of vapor. This volume is shrinking and there is a mass flow out, and we need to get a grip on that mass flow before we can solve the energy flow, because the energy leaving is attached to the amount of mass leaving per second. Thus we first set up a mass balance, which reads as the ddt of the liquid mass. It is, let me mark that in red, it is the control volume, is the liquid, not the cooker. So what I wrote here is that the mass inside my dashed red control volume, which is the mass of liquid, is changing not because there's inflow, but because there's outflow, and obviously there's no production of water. Thus I can use at any time that the change of the volume is connected to the outflowing mass, which I don't know yet. I can also set up my energy balance over the same control volume. Now I have that the energy contained in the liquid, which is best written in terms of enthalpy, H. This is the amount of energy in the liquid available in terms of enthalpy, equals what flows in, which is 0, minus what flows out, plus what you produce, and this is the heater. Okay, so I have here a differential equation for the energy. But I need to connect these two. And the amount of heat flowing out with this mass is the enthalpy of the vapor times the mass. That vapor flowing out has enthalpy which differs from the liquid. It is at a higher level, and the difference, of course, is the enthalpy of evaporation. So the heat flowing out is directly proportional to the amount of vapor that flows out times the energy concentration of the vapor in terms of an enthalpy. This part, the liquid enthalpy, is a constant. It's a function of temperature and pressure in essence, but as we're working at boiling conditions, it is at 100 degrees, can be taken out, and thus I can write that part as H liquid times the changing mass, because that's what I am left with, right? I take this part out and move it in front. That's what I do. But here I can use my mass balance. This is equal to minus the mass flow rate. That's what the mass balance said. Okay, if we now combine these two, see what happens. I move that down here. I move the flows to the left-hand side. So I have this part moving with its minus sign to the left, becomes phi m, the mass flow rate, times the energy of the vapor, so the enthalpy, and I need to subtract, because this had a minus sign, phi m times h of the liquid, and this equals what is left on the right-hand side, which is p. I can simplify this, take stuff together. And I can realize that this is, of course, the change in the enthalpy if you evaporate. And thus I have backed out that the mass flow rate equals P over the delta H of evaporation. Now I can go back to my mass balance, because I now have this term, and I can equate the change in mass. So I'm going to write that back. The change of the mass of liquid, that's what the balance here said, equals minus P over delta HEV. This governs the evaporation. This is a simple equation that can readily be solved, and that turns into that the total mass is changing over time proportional to this number. Do I have a spot left? I can write that probably here. No, probably not. Okay, what do we do? I'm going to scribble it in here. If you solve this equation, you get that the mass of the liquid equals the starting mass, which is our half liter turns into half kilogram, minus P over delta H EV times time. That is the solution of this equation with the initial condition that we know the mass at T equals 0. At the end, this one is 0. And compare what you have here with our quick and dirty, and you will obviously find the same answer. Quick and dirty works always fine if you find a quick and dirty solution. This is how you do it when you use balances and when you can make a formal derivation. Advantage here, as it's quick and dirty, that you're quick. Disadvantage is that it's kind of dangerous. If you gamble on the wrong quick and dirty, it's going to be wrong. Disadvantage here that it is long and mathematical. Advantage is that I can clearly see where are my assumptions. Assumptions are sitting here, that nothing is flowing in and there is no water produced, not a real big assumption. Assumption is here that there are no losses. The only loss is via the vapor that's going out. If you really want, you can refine this. I leave that up to you. If you cannot follow this example completely, don't worry. It's to show you how you can use these balances. If you don't understand the concept of enthalpy, you will probably find this very difficult. But at least I hope I showed you how you work with two different balances and how you can use one into the other to get a grip on what happens here.